Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now I'm just going to get started for our questions in today's session. Okay, so question 1 asks, is the process of liquid water turning to ice endothermic or exothermic? Explain what is occurring using the terms system, surroundings, heat, potential energy, and kinetic energy in the discussion. Okay, so before we answer this question, let's make this like a comparison table for endothermic and exothermic. Big. Okay, so during an endothermic reaction, heat is absorbed from the surroundings to the system. So this is the same thing as saying that heat is a reactant. Also with endothermic reactions, the sum of enthalpies of products is greater than the sum of enthalpies of the reactants. So this can also be expressed using these variables, where the sum of the enthalpy of the products is greater than the sum of the enthalpy of the reactants. Okay, so now let's look at exothermic reactions. So here, heat is given out to the surroundings. And this is from the system. So this is the same thing as saying that heat is a product. Similarly, the sum of the enthalpies of the products this time is less than the sum of the enthalpies of the reactants. I'll also note that for an exothermic reaction, the delta H of reaction is less than 0, so that means it's negative. And in endothermic reactions, the delta H of reaction is greater than 0, so it's positive. So the question asks if the process of liquid is endothermic, of liquid turning to ice is endothermic or exothermic. And this is actually an example of an exothermic reaction. So I'll just write it in the column for exothermic. And let's draw like a little diagram. So this is liquid water. That's is frozen to solid ice. So the reason this is exothermic is because the system loses energy which is transferred to the surroundings in the form of heat. So if we think about the opposite of this reaction, turning ice into liquid water, in order to melt the water, heat needs to be added. So that's why solid melting to ice is an endothermic reaction, because heat is a reactant. But in this case, when you have liquid turning into ice, that energy loss is transferred to the surroundings in the form of heat. So we can also draw a potential energy diagram. So I'll draw it at the bottom here. So this is the potential energy diagram of liquid turning into ice. So this is a plot of potential energy. And then this is the reaction progress or coordinate. So let's say the energy of liquid water starts like here. The plot would look like this. So this little hump here is referred to as the activation energy. This is how much energy needed to be added for the reaction to take place. And if you notice, our reactant is at a higher energy than our product. So we can say here that heat was released. Okay, so that's an example of an exothermic potential energy diagram. So let's just compare it to what a potential energy diagram would look like for an endothermic reaction. So just drawing the same diagram. Let's say we wanted to melt ice. It will look like this. So you'll notice that our reactant this time is at a lower energy than our product, which is water. So I can label this as heat being absorbed. Again, this is just activation energy. Okay, so let's see what the junior tutor said. An exothermic process releases heat, causing the temperature of the immediate surroundings to rise, while an endothermic process absorbs heat and cools the surroundings. We consider the sample of water as our system. Freezing is an exothermic process. This is because energy moves out of the water towards its surroundings, which technically makes the water particles lose kinetic energy, making them move slower and slower as freezing takes place. Okay, so the question asks for terms using system and surroundings, which is what the junior tutor said. They mention heat and kinetic energy. Yep, the solution's still correct. Anyways, even though potential energy, that the term wasn't used, but it was still a very detailed and in-depth explanation. Okay, so question 2 asks, what is a nitrogenous base? So even just looking at the word nitrogenous base, we can gather that it is a molecule that contains nitrogen, with chemical properties of a base. This is because all the nitrogen groups contain lone pairs of electrons. Okay, so I'm going to draw some examples of nitrogenous bases, which are present in the DNA and RNA. So I'll just say example of the nucleic acids. Okay, so for example, we can have like guanine, or adenine. So these two are examples of purine. And we know that because they have two rings in their structures. And now I'll just draw all of the pyrimidines. So pyrimidines pyrimidines. So they all contain one ring. So for example, we can have uracil. Or you could have cytosine. And lastly, you can have thymine. Okay, so these are all examples of nitrogenous bases. So let's see what our junior tutor said. A nitrogenous base is simply a molecule that contains nitrogen and has the chemical properties of a base. There are two kinds of nitrogenous bases present in DNA and RNA: pyrimidine bases and purine bases. The pyrimidine bases are cytosine and thymine, which are found in DNA, and uracil, which is only found in RNA. The purine bases are adenine and guanine. Adenine always pairs with thymine or uracil, and cytosine always pairs with guanine. Yep, so this solution is correct. Okay, so question 3. Okay, so question 3 asks, complete the periodic table pun. What do you blank to a wrinkled shirt? So do you A, AC stands for actinum, B is tungsten, C is iron, and D is arsenic. So the answer to this question is you iron, which is Fe, a wrinkled shirt. Great question. And the junior tutor said the iron is Fe, You iron. Answer is FE. You iron a wrinkled shirt. Yeah, so this solution is correct. Great job. Okay, so question 4 asks, what is a concentration gradient? So this is when the concentration of particles is higher in one area than another. Okay, so an example of concentration gradient would be like passive transport. So passive transport takes place in like our bodies. Basically, this is when particles diffuse from a high concentrations to low concentrations. And this happens until it is evenly spread out. So let's try to draw out a diagram of passive transport. This is like supposed to be a membrane. This kind of is like the pump. And let's say the left side has a high concentration of sodium ions. And the right side only has a few concentration of sodium ions. So what happens is that these sodium particles want to diffuse. Since there's such a high concentration on the left side, they want to move over and go on to the right side. So now I'll just kind of draw what this will look like after. So this happens until they're all evenly spread out. So this is an example of like a concentration gradient. Let's see what the junior tutor said. Concentration gradients occurs when the concentration of particles changes over a distance. For example, a few drops of food dye in a glass of water diffuse with the concentration from where the dye exists in its highest concentration, for instance, the brightest blue or red, to where it occurs at its lowest concentration, where the water is still clear. The diffusion will continue until the concentration of the dye becomes uniform in all directions of the water. Concentration gradients are the chemical driving force behind many processes that take place near cell membranes. Yep, so this solution is correct. Okay, so question 5 asks, is boiling water a chemical change? So first let's define what a chemical change is. Chemical change is when a substance is chemically transformed into one or more different substances. So an example of a chemical change would be like iron turning to rust. So to answer this question, no. Boiling water is actually an example of a physical change. And we know this because the water, when it is exposed to high temperatures, turns from a liquid to a gas. But the gas that is produced is still H2O vapor. So it doesn't really change into a different substance. It's just a phase transformation, pretty much. So the junior tutor said, no, this is an example of physical change because no change in the chemical properties occurred. That is, no chemical reaction occurs, nor is there a change in the chemical properties of water when it is vaporized. The water vapor molecules are still the same chemically as the liquid water molecules. Yep, so this solution is correct. Question 6 asks, how do you calculate the standard enthalpy of reaction delta H for the following reaction? Okay, let's write down the balanced reaction. 4 NH3 gas plus 5 oxygen molecules makes 4 NO plus 6 H2O. So notice that they also give us the delta H formation values for all of these compounds. So I'll just write it in blue. For NH3, it is negative 45.9 kilojoules per mole. For oxygen, it is just a pure gas, so it is 0 kilojoules per mole. NO is 90.3 kilojoules per mole. And lastly, H2O, negative 241.8 kilojoules per mole. Okay, so to answer this question, I'm just going to write the basic expression on how to calculate the standard enthalpy of reaction. So the delta H of the reaction is equal to the sum of the delta H of formation for the products minus the sum of the delta H of formation of the reactants. So notice that I put N in front of all the delta H values. So this shows us that the number of moles actually has an impact on what our final answer will be. So let's plug in all of our values. Starting with the products, there are 4 moles of NO, and I'm going to multiply this by its delta H of formation value, which is 90.3 kilojoules per mole. Then water is also a product, so I'm going to add 6 moles times negative 241.8 kilojoules per mole. So these are all of our products, and then I'm going to minus the sum of the delta H of formation for all of our reactants. So our reactants is the 4 moles of the NH3. So its value is negative 45.9 kilojoules per mole. And then lastly, we have the oxygen. So there's 5 moles, but its value is 0. So we know that this will just cancel out. I'm just going to draw this canceling out. So now we just need to calculate, sum everything up, and make sure you want to do all of the multiplication steps before adding all the values up, just so that your calculator doesn't get confused with all the different values. And you should end up getting a final answer of negative 906 kilojoules. So you'll notice that the moles will cancel out when we multiply by all the coefficients. So let's look at what the junior tutor said. Recall that the delta H of reaction is given by this formula. Delta H reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Since we are given the standard enthalpies, we can solve this directly. Remember to consider the coefficients during the reaction. So they had the 4 times 90.3 plus 6 times negative 241.8, all of that minus 4 times negative 45.9 plus 5 times 0, and they also got negative 906. So this solution is correct. Okay, so on to question 7. Give the conjugate acid for each compound below. So conjugate acids are species that are formed after a base gains a proton. So let's just have an example of this. Okay, so let's say we had HCl plus water makes H3O plus Cl minus. So in this example, HCl is an acid. And we know this because it is the proton donor. So it gave one of its protons to the water. So water in this case is our base. And again, it is just our proton acceptor. So after the base gains the proton, it becomes H3O plus. And this is our example of the conjugate acid. And for chlorine, Cl minus, this is our conjugate base. So it is the species formed after the acid donates a proton. Okay, so now let's answer the question. So starting with compound A. So let's say this is our base. If it were to gain a proton, it becomes hydrogen sulfide. Okay, so that's the answer for A. HPO4 minus, or 2 minus, sorry. When it gains a proton, it becomes H2PO4 and then just minus 1. And then lastly, NH3, when it gains a proton, it becomes NH4 plus. Okay, so let's see what the junior tutor said. An extension of the Bronsted definition of acids and bases is the concept of conjugate acid-base pair. Recall that the Bronsted definition of acids and bases is about the ability of a substance to donate or accept a proton. A Bronsted acid is a substance that can donate a proton, while a Bronsted base is a substance that can accept a proton. Conjugate acid or conjugate base is then the species after the initial acid loses a proton or is the deprotonated acid. This follows that the conjugate acid is the species after the initial base gains a proton or is the protonated base. With that in mind, we can answer the question. Since we are given bases and are tasked to give the conjugate acids, what we have to do is to protonate all of the species. When HS- is protonated, we get hydrogen sulfide. Since we gave a proton, the sulfur will be bonded to 2 hydrogen atoms and will become neutrally charged. When we give a proton to HPO4 2-, the formed species is H2PO4-. The charge would increase by 1 since one of the oxygen atoms will now be bonded to the added hydrogen atom. Lastly, when we protonate NH3, the result is NH4 plus. Thus, the conjugate acids are H2S, H2PO4-, and NH4 plus. Yep, so this solution is correct. So moving on to question 8. What is the chemical formula for diamond? So diamonds don't really have a specific chemical formula that we are used to, but basically it is an allotrope of carbon. So this, in other words, means that it contains repeating units of carbon. So similar to diamonds are also graphite. So it is also an allotrope of carbon. So the reason why they have such different structures is because of the type of bonding, carbon bonding, that is in each of the allotropes. So let's see what the junior tutor said. Diamond is a solid form of the element carbon, with its atoms arranged in a crystal structure called diamond cubic. At room temperature and pressure, another solid form of carbon known as graphite is the chemically stable form of carbon, but diamond almost never converts to it. It has a chemical formula C. Distinction in terms of naming graphite and diamond is done. Yep. So this solution is correct. Okay, so now let's move on to question number 9. What do you mean by back titration? So back titration has 2 steps. The first step involves the addition of excess standard titrant to the analyte. And the second step is then you have the titration of your excess titrant to determine exactly how much excess was added. Okay, so let's see what the junior tutor said. Titration is a technique to determine the concentration of an unknown solution. In any titration experiments, there are several parts of the titration setup. The titrant is the solution of known concentration, which is added to another solution whose concentration has to be determined. The analyte is the solution whose concentration has to be determined. So back titration is a type of titration that involves the addition of excess standard titrant to the analyte and then the titration of the excess titrant to determine how much is in excess. Oftentimes, back titration is used if the analyte is an insoluble salt, a particular reaction is too slow. Titration would include weak acid, weak base titrations, which is difficult to observe the endpoint, and one of the reactants is volatile and some might escape during the titration. Yep, so the solution is correct. Question 10 asks, how many quarts are there in a gallon? So there are 4 quarts in 1 gallon. And our junior tutor said, solving for this, 1 gallon times 4 quarts over 1 gallon is equal to 4 quarts. Therefore, 1 gallon is equal to 4 quarts. Yeah. Pretty straightforward. Solution is correct. So question 11 asks, how much does 1 gallon of water weigh? Okay, so first let's recall that 1 gallon is equal to 3.785 liters. And 1 liter is equal to 1,000 milliliters. And also, which is gallons, will be in the denominator. So now I want to convert my liters to milliliters. So now I'm going to put my milliliters in the numerator. So 1,000 milliliters over 1 liter. And then lastly, converting milliliters to grams. So this is the density of water. So 1 gram per milliliter. And then you'll notice that our units will cancel out. So the gallons cancel out, and then the liters. And then lastly, milliliters. Then this gives us a final value in grams, which is 3,785 grams of water in 1 gallon. Okay, so let's see what the junior tutor said. Weight could mean 2 things. It could either mean how it is used in day-to-day conversation, which is the amount of mass of a substance, or it is used in physics, where weight is the force exerted on a body by gravity. Let's think about the former. This means that to get the weight of water, we need to perform a series of conversions from gallons to the unit of mass, which is kilograms. First, we need to convert gallons to liters using the conversion factor 1 gallon is equal to 3.785 liters. Then we convert the amount in liters to meter cubed. The conversion factor is 1,000 liters is equal to 1 meter cubed. Next, we will assume that the water is at normal temperature and pressure. And to obtain the mass, we need to convert the unit of volume, meters cubed, to a unit of mass using the density of water at normal temperature and pressure. So they use 998. I just used, well, in this case, like 1,000 kilograms per meter cubed. So they combined all the steps and ended up getting 3.77743 kilograms. So this is pretty much similar to my answer as well. Thus, a gallon of water has a weight of 3.77743 kilograms. That said, we can also consider the second meaning of weight. The unit for this is kilograms times meters over second, or N. For this, we multiply the mass of water obtained above to the acceleration due to gravity, which is 9.8 per second squared. Get the weight. Okay, so they just multiplied by 9.8. All right. So this solution is correct. So moving on to question number 12. How many torr is there in 1 ATM? So 1 atm is actually equal to 760 torr. This is the standard pressure. Let's see what the junior tutor said. Torr is another pressure unit which is described 1 standard atmosphere divided by 760. This means that 1 torr is equal to 1 over 760 atm, or 1 atm is equal to 760 torr. Torr is often used for measuring the pressure of the high vacuum. Yep, so this solution is correct. And I think we have time for one more question. Number 13 asks, what is the molar mass of urea? So first I'll draw the chemical structure of urea. Which is shown here. So now let's determine its chemical formula. So there is 1 carbon, there are 4 hydrogens, and 2 nitrogens, and a single oxygen. So now we want to calculate the molar mass of urea. So to do this, we would need all of the individual atomic masses of all of the atoms that are involved. So in this case, carbon, hydrogen, nitrogen, and oxygen. But we also want to take into account how many atoms of each element are in the compound. So for example, the molar mass of urea is going to be equal to the molar mass of carbon plus 4 times the molar mass of hydrogen, since there are 4 hydrogen atoms in urea. Similarly, we're going to multiply 2 times the molar mass of nitrogen, and then just add the molar mass of oxygen. Okay, so all of these atomic masses are just found on your periodic table. The molar mass of carbon is 12.01 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. The molar mass of nitrogen is 14.01 grams per mole. And lastly, the molar mass of oxygen is 15.99 grams per mole. So now I'm going to add all these values up, and I end up getting a final molar mass of 60.06 grams per mole for urea. Okay, so let's see what the junior tutor said. Molar mass is the mass in grams or kilograms of 1 mole of a unit of a substance. For a molecule, we just get the sum of the molar masses of the individual atoms. The molecular formula of urea is CH4N2O. The molar masses are 12.01, 1.008, 14.01, and 16.00 grams per mole for carbon, hydrogen, nitrogen, and oxygen, respectively. Thus, the molar mass of urea is 60.062 grams per mole. Yep, so this solution is correct. Okay, so I think that is all the time that we have for today's session. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a like and a comment. And don't forget to share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.